So we've talked about manager, we've talked about policy. What else do we have to get into in the larger architecture discussion? Well, let's talk about the controller. The controller function of the NSX management node is the centralized portion of the control plane of NSXT. It gives us all of our basic runtime functionality as well as, well, it gives us a means to talk to all of the different data plane components and program them. The controller function is, well, it's kind of a critical component here, because manager hands off instructions to the control plane, to controller, and the controller then goes and publishes that data to, or programs rather, the data plane with that information. So the control plane is actually broken up into two pieces, right? We've got the central control plane and we've got the local control plane. And the local control plane is the part that actually does the programming of the data plane. The central control plane simply distributes information out to all of the local control plane nodes. So where does the local control plane live? Well, the local control plane lives on a transport node. It lives on an ESXi host. It lives on a KVM hypervisor. It lives on an edge transport node, for example. So the control plane is both centralized and it's distributed, right? It's a very interesting thing to think about there. The central and local control planes, as I kind of just spelled out, and as we sort of spell out in the first point on this slide, provide two very different functions, right? The central control plane is the central repository for the runtime state. This is where everything comes back to be curated. And we'll see a bunch of this stuff as we go back and talk later about logical switching and logical routing and so on and so forth. We'll reference a lot of times, we'll reference things like, and this is sent back to the control plane. Well, what does that mean? That means it's sent back to the central control plane. All right? So the central control plane maintains that runtime state, and it pushes the information that needs to be programmed down to the local control plane. The local control plane then knows how to deal with the user space and kernel space agents and modules that live on the actual transport nodes to actually program those. The local control plane, since it is local to the transport node, has access to things like link data for physical NICs on the hypervisors and so on and so forth. So it can monitor the health of the transport node as well. So there's a lot of information there going back and forth depending on what we're looking at, right? And I want to bring up one very, very important point. It's the last thing that we talk about on this slide, right? The local control plane pushes stateless configurations to forwarding engines. The actual data plane itself, that we'll talk about in a different video, the data plane itself is stateless. The data plane does not carry any information, so that if a transport node fails, and the data plane on that transport node therefore fails with it, what happens? Well, nothing, right? When that transport node returns to service, we're going to push that state back to it from the control plane. So the data plane, the forwarding engine, is stateless. That's a very important thing to remember. All of the state is carried in the central control plane. Now, every transport node, every local control plane node, has one central control plane node that is responsible for it. And as such, a given transport node will be controlled by one controller node. Remember, I've got 3 controller nodes. I have one controller node in each of my manager appliances. So when I look at my transport nodes, they're going to have a connection to one of my 3 controllers. Not all 3 of them, only a single controller. And that connection is where, say, a change, right, that may take place on a data plane node. A change may be propagated back to the central control plane. That central control plane will then have to distribute that change perhaps to other transport nodes. Well, that's what we're looking at here. I have my transport node sending an update to the controller, well, that one controller is also responsible for another transport node. So we see the line pointing down to the middle ESXi or KVM host, where my receiving controller is also sending information. But the third transport node has to get that change information as well, right? Maybe it's a state change. So that third transport node needs to get that as well. Well, the third transport node is not connected to the first controller. The third transport node is connected to the second controller. So the central control plane synchronizes among itself so that that second controller can then propagate that information down to the third transport node as well. So we need to think about this. This all happens seamlessly and near instantly. So timing is not a big concern here, right? This isn't it's not like we're looking at this and talking about a delay in seconds, right? This is near instant. So we don't have to worry about this from a day-to-day perspective, but understand that each transport node is for lack of a better word, controlled by a single controller node, not by the cluster itself, even though the cluster acts as a single whole, right? That way we can distribute the controller load across the three different controller nodes. Now, what we're describing here, what I'm kind of talking about here is this function we have called sharding. And sharding is simply the workload distribution of my controller. So my controller nodes kind of talk to each other, and they say, okay, we've got all of these different transport nodes. Who's responsible for what transport node? And the control plane just works its magic under the hood, if you will, and works through its algorithms and distributes the transport node shards to individual controller nodes, so that controller 1 is responsible for, in this example, 2 transport nodes, and controller 2 gets responsibility for 3 different transport nodes, controller 3 for another 2 transport nodes, and everything just functions. Everything just operates, right? The controller nodes themselves synchronize data between one another so that all of my transport nodes can have whatever the same information they need to have. So, what does that mean when a controller fails, right? Because, let's face it, things fail in the data center, right? Virtual machines fail from time to time. Hypervisors fail and cause a virtual machine to be restarted with vSphere HA or whatever might happen. If a controller node fails, all we do is redistribute those shards, right? Each controller knows which of the other controllers or which transport nodes the other controllers maintain, right? There's a larger sharding table that everybody knows about. And all we're going to do when a controller fails is redistribute the shards that were on that controller node to the surviving controllers, right? Now, that will cause the data plane node to, reconnect to the new controller. So there will be a blip in the control plane, but understand this will have zero impact, no impact at all on the data plane, right? Virtual machines will keep doing their thing, traffic will keep flowing, firewalls will keep working, right? The data plane is completely unaffected by this. This is simply a quick reconnection of the control plane for a couple of transport nodes to new controller nodes. That's it. So this is how we're distributing the workload of the controllers across the controller cluster. So what's the takeaway here? Well, controller, I've got a central and a distributed local control plane that I have to think about. And the control plane is what's programming the data plane, right? The control plane, the central control plane sends information to the local control plane. The local control plane programs the local data plane. So there we have it. Come back. We'll take a look at the data plane in the next video.